non-transversal interpretation for a non-global smooth recovery.
Okay, thank you very much to organizer for inviting me. Let me say a couple of things before starting. So when I was out from home, my wife says, "What are you doing going to a conference if you cannot walk?" And look, here I'm sitting in the chair. And while I was preparing the talk, I was thinking, well, I can do this in the blackboard. I can do this picture in the blackboard. And then I realized that I can't go to the blackboard. And the third thing is that when I opened this file to start the preparation of the talk, that was Friday morning, Nuria was with Robert talking about preparing the talk of Robert. And then she says, it's important that you notice that a talk is not a paper. And then I start doing this, and I realize that the title I put it is horrible title. It corresponds to a paper of a title that I don't agree because it's too large. But it is the reason of the title is for my co-authors. So let me finish by saying that I add this connection to other fields, because when I was preparing the talk, I realized that this is not Julia said or whatever. So I add this thing. I think this happens in Shenzhen, so I could feel. But the first talk of this conference, it was about something which was not in the Julia said so. Let me go. Let me see if I can do this. So it works, huh? 1 more minute ago. Okay. Now, so this is about, if you want to solve given a polynomial that it has some expression and you fix the degree of the polynomial is d plus 1, because as you will see, d will play an important role in this talk. So d plus 1 is the degree of the polynomial. And then a way of solving the equation p of x equal to 0 is, among others, it is doing these iterative methods, that you plan a dynamical system so that the asymptotic behavior of most of the orbit, or at least some of the orbit, goes to one of the roots of the polynomial. And this could be of dimension 1. So you have a unique initial condition and you get a new, so you move from x0 to x1 and from x1 to x2, etc. But it also can be, you start with 2 initial conditions and then you create an IT1 and you do a dynamical system and then you get a higher dimensional dynamical system. So even though not all the community agrees with that, dealing with root finding algorithm from the dynamical system point of view, it is something that it could be nice. So this talk is not going to be about that, but meaning let me put this in a framework, not start by a map for nothing. So if you have the typical, well, you have a polynomial or something that it looks like a polynomial, it's not, the picture is not really good, but something, and you are trying to find the roots of this, so this point in here, a way of doing that is to use the secant method, which is a variation of the Newton method when you a priori have no derivatives. And this is this formula that basically says that you take 2 initial conditions, x0 and x1, and you see which is the next cut of the line with the real line, and then you get x1 and x2, and you do the same, and you get x3. So for 2 initial conditions, you get a new one, and this is a dynamical system of dimension 2. Well, meaning instead of looking at this from the point of view of the reals, you could write this down as a map, which goes from xy, that will be the initial condition, and it gives you the next point, which is y, because remember, x0, x1 goes to x1, x2, and this is the expression of x2. Okay, so this is a formula that it can be written in different ways. Of course, this formula has a little problem because the denominator could be 0 at the point where xy which in p of x is equal to p of y, that it could happen when x is equal to y, that for sure happens, but it could happen for other x and y because my polynomial, it's not a different, it's not a bijective. So in any event, if this method is good because the fixed points of this method, alpha alpha, because this is a 2-dimensional, if you have a fixed point, this fixed point corresponds to the zeros of the polynomial. That's good if we are thinking in an iterative method. And let's say that we agree that, well, you can prove that these fixed points are not only fixed, but they are attracting. I'm assuming for the whole thing that my roots are simple for the polynomial p, because if they are not simple, they are multiple, then other things happen. We already studied some years ago. but it doesn't matter. So in this talk, let's say that alpha is going to be always a simple root. And then this is an attracting, where I call it A of alpha as the basin of attraction in the plane. And the idea is to study which properties it has, this basin of attraction. Well, this is the basin of attraction, and this is the immediate basin of attraction, but in this talk, this is not matters. So let me start by giving you a picture of this, the dynamical system for some cases. Notice that now the degree of the polynomial is 4 in the left, and I try to do this in color. So this is 1 color, 2 colors, 3 colors, 4 colors, the 4 roots of the polynomial. I'm thinking in roots of the real roots of the polynomial, roots that are real of the polynomial. This can be understood also in the complex case, but this is C2, too much for me right now. So I'm thinking in the dynamical system, as a dynamical system is in R2, and then the natural things to find are the real roots of the polynomial. Here is with 4 roots, here is with 5 roots, 5 colors, and you know, it looks different from the typical picture that we have for the Newton or something. Well, and we study this for many years from different point of view, but today I will try to focus my attention. You see this, the colors are the ones that corresponds to the roots of the initial condition that goes to the roots of the polynomial. But as you see, there are some white regions in the middle also appears. So you produce this picture by saying to the computer that if nothing happens when you are iterating, then draw in white. This is my colleague doing this. And then look what, so if you focus in the white regions, look, this is a white region that corresponds to degree 4. And this is another, so look at the shape of the white regions here and here. It is kind of different. And let's see if I can explain how this managed. This white region corresponds to initial condition that would not go to any of the roots. So that's bad initial conditions. And as we did in Newton, we are interested in understanding what happens in those cases. Well, it follows from Bedford and Fritsch that they made this paper on the secant map from a dynamical system point of view. That's exactly the title of the paper, and that would be the title. It should be the title of my talk. But what they show is that, you know, if you have a point which is a 0 of the derivative, but it's not a 0 of the polynomial. So this is my polynomial has simple zeros, and then the 0 of the derivative are other points, more or less in between, say. Then what happens is that if you look at the secant map, you put some good, you extend the map to the infinity because, well, you need the infinity because as you will, well, you see that the orbit of this point, which is x0, x0, no, as alpha, alpha was a fixed point for the secant map, then x0, x0, it's a point which is not one of the roots. It moves to x0 infinity. This is why we need to extend this to infinity by using local coordinates. And then this moves to infinity x0 and it comes back. So it gives you a periodic point of period 3. It happens that the secant map has no periodic point, finite periodic points of period 2 and 3. So so it is either a fixed point or a periodic point of period 4. Has no periodic point of period 2, has no periodic point of period 3, but it has this, what we call it a critical periodic 3 periodic cycle, which is the one using the critical point of the polynomial and infinity. Well, and the idea was to understand this guy. Well, what they prove, Bedford and Fritsch, they prove that if you look at the third iterate, so you do the local coordinates and you look at the third iterate at a point near the x0, you get that this is basic. Well, he moves, well, they move first the 0 to 0. So notice that the derivative is equal to 0 at 0. So now 0 is my x0 here. So 0, 0 goes to blah, blah, blah. And then you look at the local expression in terms of the third iterate, because this is a period 3 point, and you see that this is the expression. So it has a linear part, which is kind of, well, it is not, how to say, elementary, because you have y. And then the first period, the first term that appears is of degree d, and this is why the d, it is the d here, and d plus 1 is the degree of the polynomial. So according to my degree d plus 1 of the polynomial, you have a d here, plus higher order terms. Well, what happens is that the differential of this map has 2 eigenvalues, which is 0 on the one hand, and lambda 2 equal to 2. So it is not like the identity, parabolic, but it has a 0 and a 1, and we want to study this guy. Well, here is, let me say that I take a polynomial of degree 3, so d plus 1 is 3. Now it's d is equal to 2. And if you look at the white region, this is my 0, 0 in this one for this polynomial. This is 0, 0. And here you see this Nike shape looks of the basin of attraction. Here is a zoom of this. While if you go to degree 4 for the polynomial, degree 3 for my cutting map, say, then you see, this is the white region, and this is an extension. Well, this extension, it looks like it goes to this point, and that point. That points are indeterminacy points, or we call it focal points, for which you cannot extend the map. Somehow, in terms of S, they are at infinity. I mean that you cannot extend the map at those points because they are, in terms of algebraic geometry, I think they call it indeterminacy points, zeros of the denominator, okay? Well, what we do is let's focus in the model. So we cut the higher order terms, and we want to study this map as a map on the plane. So the goal of this, I don't know how many minutes I have, 40 minutes or less than that, is to try to give you some information about this map. Well, if you look at this map and you draw numerically this the basin of attraction of 0, so 0 is, of course, is a fixed point, and depending on the degree, so this is d equal to 2, so the polynomial has degree 3, you have this Nike shape thing, and the 0, 0 is, it looks like it is in the boundary. It is, but it's not only the numerics, you can prove it. And in this other case, where d is equal to 3 or odd, and then the degree of the polynomial is even, then this is 0, 0, it is in the middle, so the basin of attraction as a regular set. And if, well, and there are two cases, that depends on A. Here they were, this question here, notice that if D, it is even, okay, you can think that A, D plus 1 is 1. So the important thing is that when D is even, then you have, this has, no matter the sign of A2, this is always positive. So there are some restrictions, but we substitute this term as an A, because we don't care now anymore. And you have this map with A different from 0. And then if, let's say, D is even, no matter, and A is 1, you have this. Well, because you can reduce this case to A equal to 1. So A equal to 1 minus 1 cannot exist. And these are the odd cases for which you have a case A equal to 1 and A equal to minus 1, that then when you look at the basin of attraction or whatever it is attracted by 0, you see just a curve. And we more or less want to understand this thing. Okay, this is the A of 0. Now it substitute this the basin of attraction of the fixed point of my map. Okay. So understanding, let's say, these pictures, when you cut it for D, it looks like it could help to understand, for instance, this one, which looks very, very thick. Well, here, what we first do is to see what happens locally. I mean, we study the point locally and the stable and unstable manifold from the point of view of real dynamics. And then we see, well, this is not the point of this paper. I'm just saying that, for instance, in this case, everybody enters, because in this case, there is a central manifold. This case has a central manifold, and this also too. And then in this case, the central manifold attracts, so everybody attracts. And then locally, you have that everything is red, while in here, you have, this piece that is go out, so the point is in the boundary, okay? And this case, you have this is the stable manifold, while the central manifold is unstable, and this is the reason why you only get basically the stable manifold associated to the point. I will focus for the rest of this talk on this case, okay? My goal is this blue point, and then I will focus on D odd and A equal to 1. From now on, I will not say anything again D, because D is going to be odd forever, well, forever in my talk, and A is going to be 1, according to this map that I draw it here, okay? Good. So let's see what we can say about that. Well, I just give again the pictures. This is the model that we have. cutting all the higher order terms. And this is the picture we get as a basin of attraction of 0. And this will represent the basin of attraction of this white region by the third iterate of my secant map, which is this white region. Well, notice that, meaning, well, we will see, at least we will state that this basin of attraction is unbounded. It goes back and forth. And, in some sense, as I tried to tell you before, this is also unbounded in the sense that it looks like it goes towards the points that are at the end of the domain of definition of this tree. And it is nice, and we don't know how to connect right now, so I'm going to talk other things, but I just pointed out that, we cut it here at higher order terms. So a priori, this has only value in a very small neighborhood of 0, 0. While when you look at the whole picture, this whole picture, it looks like a lot this, but in a global sense. So we don't know how this local map is able to express what happens in the dynamical plane of the secant, but not from the local point of view, but from the global. Well, global, I mean that bounded away from 0, okay? So here is this D and this D plus 1, as I told you. Well, so let me talk about, so we fix the D, we fix the A, and then let's see what are the important things that will happen here, because eventually I should end to my title, and right now there is no title at all, nothing about the title, but I will go. So for this case, what is important is that I don't know, you made some computations and you realize that 0, 1, which is P0 from now on, and 0 minus 1, which is P1 from now on, they are a periodic orbit of period 2. So it's P0 goes to P1 and P1 goes to P0. That's one thing. And you can compute the eigenvalues of this cycle, and it corresponds to a hyperbolic saddle, say strong hyperbolic, because it has an eigenvalue which is really small, and let's say 0.01 or something like that, and an eigenvalue which is really big, like 54. Well, that depends on D, but for D equal to 5, it is 54. So it is expand a lot in one direction, and it contracts a lot on the other direction. Well, it is also it's good to know that, well, we are using this a lot in the construction or in the arguments, is that this map, for this specific case of D being odd, it is an invertible map. It's it is 1-to-1, but it is not a global dieomorphism. This is the first time that you get a hint of the title of the talk, non-global, blah, blah, blah. So it's not a global dieomorphism. When you compute the T minus 1, you get this X minus 1 over D. So when X is equal to Y, you have some troubles with the differentiability of the map. So it's not a global dieomorphism, but it's 1-to-1, and everybody, it is going from one point to another. And if you cross X equal to Y, then you have a problem. Good. Well, the first result that we proved, and this is I'm not going to discuss this here. It is this result that says that for this case, the basin of attraction, it's an open, simply connected, and unbounded set. So, so what, meaning in some sense, let me just refresh in 1 minute. What you see is that 0 is clearly in the interior. We get that from the local point of local behavior. It is open. It takes a little bit of time to see it's simply connected, and it's unbounded. You use these guys that are just going to infinity, but you don't see back and forth. So you can construct these nested intervals where you cut the piece of a piece of the immediate basin of 0. So in this case, immediate basin and basin is the same because it's only one connected component. Okay, this is the first thing we did, but this is not what I want to talk about. I want to talk about the bound. Oh, yeah.
Go to the infinity. Is that the central manifold or the stable manifold?
Well, this is related with the stable manifold of P0. We will see this because now I'm going to study the boundary of this set. So this is the set, and let's study the boundary. Well, meaning studying the boundary, you can always, nobody can stop you studying the boundary, but it has some connection with the other case, T even, where this is very different from the one I'm going to show. So it's kind of it's not a dichotomy, but It is different. And this is the result I wanted to mention. I gave some hints. So the following statements hold. So the boundary of A0 contains the stable manifold of the two cycles lying in the boundary. So it contains the stable manifold of the cycle. Contains the stable manifold of the cycle point lying in the boundary. So the boundary contains, okay? So if you were in Sensini and you follow my talk, that was the result that we had at that moment, and we didn't know if there were anything else on the boundary. So we knew that the boundary includes the stable manifold of the cycle, but we didn't know if there were anything else. And the new things from Sensini to Betlebo is that we can prove that the boundary also contains an invariant Cantor set where the dynamics of the square, because I need to do T square because, you know, this is a cycle of period 2, so I do T. So from now on, I am all the time using T square. It's conjugate to the full shape of n symbols, or at least 2 symbols. It doesn't matter because the thing is that in particular, the boundary contains infinitely many periodic points of arbitrary high period. And I mean NEN. NEN. But 2 symbols is enough because what we wanted to show is that there is something more than the stable. So the dynamics on the boundary, it is, say, chaotic in the sense that for some points, they are the stable manifold of P0 or P1, so eventually they converge to those points, while you have in the same boundary points that are just wandering around. Or being periodic or aperiodic or whatever, yeah.
Is that hyperbolic?
Sorry?
Is that invariant Cantor set hyperbolic?
I think so, yeah. Yeah, because it comes from this construction. I will try to explain that this is as a corollary of the construction, I think. Let me just point it out that if you go back, that's, you know, this, if you study, we also study the boundary of this other case, not this blue, but this other case. And if you look at the dynamics on the boundary, it is precisely converging to the point. So in that case, the basin of attraction is closed because not only the points inside, but the boundary points also converge to 0, which is in the boundary. This is a different situation. So the dynamics in the boundaries, this is trivial. Everybody goes to 0, while in this case, the boundary has a chaotic behavior with, according to this cycle plus this Cantor set. And all the rest that you get when you close. Okay, so this is the new thing if you move from Sensini to Betlebo. Let me see if I can finish by showing a little bit how to prove that, or at least how to attempt to prove that. Well, first, let me say 1 minute about how we prove A, so that the stable manifold is inside the boundary. What we prove already is that this blue line, which is 0 minus 1/2, it's always in the basin of attraction, no matter D. So from now on, D, it is odd, I think I said, odd, and it no mention on D because this works for all D. So this 0 minus 1/2 is always in the boundary. Sorry, it's always inside the basin of attraction of 0. And then we extend the local unstable manifold at P0, which is this one, and we prove it cuts here. And then once you are there, you are done. Because, you know, if you pull back this argument, this goes there, this goes there, this goes there. So P0 is in the boundary. And then when you have that P0 in the boundary, you need to prove that the whole stable manifold is in the boundary, and you use here the lambda lemma to conclude. Okay, that was the way to prove the part A of the theorem, so that the stable manifold of the cycle, it is in the immediate basin. It is in the boundary of A0, which is the basin of attraction of 0. And now I want to say something in the 10 minutes I have to finish about this other case. So here I draw it. It was funny because before proving the result, we did some numerics. Tony was working on that. And you know, this is the blue, okay, the blue thing that you see here, which is the boundary. Okay, you see that the blue thing is the boundary. It is you take the local expression of the stable manifold at P0 at P1, and you start extending by doing the pullback of the dynamics. And then you do that, I don't know, 10 times or something like that. And when you see, because remember I said it is hyperbolic, I mean, when you pull back, this 54 is acting in your favor, is 1/54. And then in 10 iterations, you get basically that is the whole boundary. So you start with a piece of the stable manifold, you just enlarge by doing t-1, and you get basically the whole boundary. So when we saw this blue picture before having a theorem, we knew that that would be our goal, to prove that the boundary, it is at least the stable manifold of P0, P1 is in the boundary. And then we also draw the yellow one. I don't know if you can see from there, but there is a yellow one, which is the unstable manifold of P0. And then again, the unstable manifold is always in our favor, because when you have the 54 again acting in our favor. So, and this is all these curves. So we observe that the unstable manifold and the stable manifold cuts in many places. So we thought to use this, I don't know, construction of Smale, Birkhoff, and Morse to have a counter set of the boundary. Well, this is the picture, but then you need to prove that this is true. Well, what we did, the first step in that direction, it was to say, okay, we were able to show that if you take, remember that this is P1 and this is P0, and I don't know if you can see from there, but there is two, okay, black and red, and there is also a black and red. So we were able to show that this curve, black and red, are concrete curves, and we were able to show that the stable manifold of P1 lives inside this guy, and the unstable manifold of P0 lives in the other one. So we were able to show that they cross. So there is an homoclinic point somewhere. But now is the second part of the statement of the title. So I said it's not a global diffeomorphism, and here we can only prove that there is a topological intersection, but not a transversal one. If you go to the Moser and the Smale and Birkhoff, they are using two things in the proof. One is that your map is a global C, so a smooth diffeomorphism. And the second is that you have a transversal intersection. And we hadn't neither one nor the other. So we need to work. That's the reason why this is a long title, because we need to somehow make an effort to go to the assumptions of the theorem that we want to apply. Okay, that would be the rest of the talk. Still 10 minutes. Huh? Okay, well, there is a slide explaining what I already said. So this is the intention is to use this result, meaning I think that formally the theorem is Birkhoff-Smale, but then Moser proposed a way to prove. I have to that it uses this. So the first version of the theorem, it uses some inequalities. You need to check that your map satisfies certain. I am not an expert on that, but you need to check that the map satisfies certain inequalities, which is difficult. And they were able, because they were very clever, to transform this in a dynamical point of view by showing that your map is a global diffeomorphism having a transversal intersection of the map, and then just go. Okay, the proof goes. Okay. Well, the assumptions, as I said, is these two ones. I insist in the same thing. And then, okay, the difficulties that we have is that we only have a topological intersection because, you know, even though, well, if you look at the picture, it is not transversal. It is absolutely, it is almost perpendicular. But you don't know if the stable manifold that goes like this, when it crosses the unstable manifold of this, it has one of the degree D odd intersection. It's like it is tangent. You cannot avoid that from the picture. Okay. Well, of course, the black and the red curve cuts transversally, but what happens inside you don't know. So that's why we only have homoclinic topological intersection. So we need to jump over these two difficulties. But let me say that T is not a global diffeomorphism, but we know exactly where the problem is. I mean, the problem. Looks at the problem, which is in y equal to x. Remember that t minus 1 has an x minus y to the square d or d square of x minus y. So you have the problem in a very concrete place. It's not a general problem that you can, well, this helps a little bit. Well, now I finish with some hints about the proof of this, at least not the formal one, because it is a little bit of computations and not disgusting. No, not disgusting. I like a lot. I mean, difficult to explain in a conference, and sitting here is even worse. So remember, this was my Q. Well, Q, I mean, I have an homoclinic point, and this is the Q I wanted to use to go towards the assumptions of Birkhoff and Smale. And this is my topological intersection. Okay. Well, you can assume that your Q, it is in, so you fix Q, P1, it's exactly the same if you go to P0, and then you assume that there is you use the lambda lemma to show that if Q exists, which is crossing between the stable of P1 and the unstable of P0, you can start with a P1, Q, which is in the stable and unstable of P1. That's easy by using the lambda lemma. So this is a topological intersection, and this is what the starting. Well, what we do is the following. Well, the first thing you should do is to, let me see if I can move. Okay. This is a horrible picture, I agree, but this is the one I was able to produce with my computer. So what's the typical, well, what's the framework of this big Birkhoff, Smale-Birkhoff-Moser situation? Here you have those, zero, let's say zero, it is in a saddle point, it's in a hyperbolic saddle point. Here you have your unstable manifold that you can think by using local coordinates, it is just a straight line. This is your unstable, local unstable manifold. This is your local stable manifold. And then this guy eventually, and it cuts. And here it is my Q, which is this transversal, in that case, because I'm in Birkhoff situation, this is a transversal intersection. And then the first thing you do is you pull back, doing the backward iteration through the unstable manifold, you produce a QU, which is a point in the say in this local near the zero, so in this line, in the line that where you know that your unstable manifold is just a line, and then you doing the pull forward, you just go and get the QS. So, so Q could be I don't know where, but then doing the push forward and push backward, you move this to this and that, and then what you do is you produce a rectangle. You construct a rectangle here, having on one side the stable manifold, on the other side the unstable manifold. But here you need certain angle. You need to control the angle where this is. So it's not only transversal, but there is some restriction of how this transversal happens. And then you get a rectangle there. Well, I will not go through this because you know most of you better than me, and I'm just giving you the hint so that what I'm going to explain later it has meaning. So and then you just push forward this rectangle because this is a stable manifold. You move. Okay, on the one hand, you shrink because of one of the eigenvalues, and you shrink -1 the other. So this is going like that, and eventually it cuts your rectangle here, and then you just push forward until you get again, and you create this Cantor-like set, and you do this forever until you have the construction. So this is what it is, and notice that there is an important map, which is the transversal map, they call it that way, which is in some sense a power. Notice that here I'm doing two things. On the one hand, I go through this piece, which is in a certain neighborhood of my zero, where everything is under control. And I don't know how many iterates I need to arrive here, K. And then there is another way, is to go and pick the other rectangle. But this is a finite, well-defined number, because that point needs 10 times to arrive here and 5 times to arrive here. So it's 50 times. So every time you go far away, and you have no control where you are going, this is a finite number of times. While in here, you could spend a lot of time until it is cuts. But it doesn't matter because everything here happens in the reals. Sorry, happens in a neighborhood where everything is under control. This is more or less what we are going to, what we want to hit in our situation. So let me, so I start with my Q that I don't know where it is. I just move my Q to nearby QS and QU as before, which are very close to my P1. that would be the QS and QU I showed you 1 minute ago. Well, that would be not, but for now on, it's yes. And this is my case. And then I'll do some change of coordinates. So I send these to the manifolds to straight lines. And then notice that here I have no linear map. So this is only a change of coordinates, no? That it is a nonlinear change of coordinates using the expressions that we have for the stable, unstable manifold as a graph of functions. But then there is a way of doing a linearization so you can kill all the higher terms so that this map is C infinity conjugate in a neighborhood of the point P1. Well, you can think that this P1 is 0 if you want, because you move the P1 to 0. So for the rest of the talk, P1 could be 0. And then you can linearize. So this is just a change of coordinates to put the stable and unstable manifold as straight lines. And then there is another change of coordinates, which is C infinity, which conjugates with the linear part so you can kill all the higher order terms. By using this linear part, we do a lot of work to show the following. Let me see. I want to produce my transversal intersections. What we do is that by using that, we know exactly what happens because this is a linear map. We construct even this linear part, which is not only lambda. So L is the linear map. It's not only L to the power of n, but you can do tau with tau positive. So you can just move like if it was a differential equation somehow, linear differential equation. And then what we do is the following. Okay, notice that it is involved. Sometimes it's difficult to explain everything. I mean, notice that in QS and QU, I have these guys, which are, so I said that there is a homoclinic intersection. So it's like, you know, here in this point, I have this intersection, and here I have this intersection. But right now, since I start with a topological point Q, not transversal like here, then the only thing I know is that here there is a topological thing. Perhaps this has some, it is not transversal, it is only at topological level. So this curve arrives here with a certain contact. But there is a curve. And then what we do is to, using this thing, we can parameterize this curve, which is in this case is the unstable. This is a piece of the unstable because this is the stable, this is the unstable. And then you just move until it hits, you know, this is, you start this and then you move a little bit and then you move until it cuts the other one. And the work is to show that when it cuts, because of the construction, it cuts transversal. So even though these points that I will start with, they were two intersections at the topological level, you can produce a sequence of points that has transversal intersection nearby. So that's the ones I'm going to use in order to go to Morse-Smale theorem. And we call it ZK and ZK tilde. Doesn't matter. That's transversal intersections, okay? So those points has a transversal intersection, you will see, because you know, this is a forward iterate of the unstable manifold, blah, blah, and it cuts the stable manifold, the red cuts this one, so this is a transversal intersection. This is what we are towards with, but we already have this transversal coming from topological. It was not easy, so I have to say that we use a result from Churchill and Roth, that they did more or less the same in another setting. So we kind of was inspired by this. And look, 6 minutes I have. Yeah, but I promise not to go more than 45 because to compensate. No, sorry, no, it's not for that. Okay, so look, these are my ZKs and ZKs I showed you before with transversal intersection. In this picture, red, it means unstable. Black, it means stable. So here you see this stable, unstable, or stable, unstable, whatever. This is the QU and the QS I start with. It was the pull backward and forwards of the Q that it goes out. And now I'll take a U, which is a neighborhood of P1, a small neighborhood. It's big in this picture, but it's small in reality, for which I know that there is no intersection with y equal to x when I have my problems of differentiability. And okay, and then important, if I want to move from QU to QS, I need only to use a fixed number of iterates, 2 and 0, and 0 is a number that happens in the paper, but a talk is not a paper, so it's a number. And if you want to move from this point to that point, remember that what we do is that we did that in the linear situation, and then you go backward through the change of coordinates. I didn't say that, but you know, once you have everything done, this is a zoom of this region, then you do that here, and then, well, in fact, we stop here because we are using these coordinates here. So once you have this in the linear, you move backward, and then you are here. So when you move from QU to QS, outside is a finite number of times. I cannot claim that I will not cut this thing. This is a far, but you know, you don't know where you are going. Perhaps you cut it, but we need to fix this eventually. Not in this talk, but eventually in the paper, yes. And the other thing is that we use the K so that, you know, the times that it uses this to go blah, 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 and to go here, it is 2K, where K, it could be as large as necessary. But when we move, so remember this, remember this transversal map. The transversal map was somehow of the iterates of a map doing like that and then like that. But all time I'm moving in this setting, I'm safe because I am I'm in P1 and a neighborhood of P1, there is no y equal to x, everything is analytic. While when I'm going out, I need to use this 2 and 0, which is a fixed number that I can control. Well, you know, okay. So this is the worst part of the talk. I will not do this because I'm so tired. But you know, once you have using these ZKs and this ZK and this ZK, notice that this piece here, it is a piece of the stable manifold. If you push forward this piece, since this is the stable manifold, eventually it should go to the P1. So this piece eventually it jumps to here. And this is my point WK, which is a forward iterate of this guy that goes there. And notice that because everything happens in a very small neighborhood of QU, because the ZK tends to QU and the ZK tends to QS, so this is in a very tiny neighborhood of this. Since this guy needs 2 and 0 iterates to go here, this needs 2 and 0 iterates to go there. So this piece under 2 and 0 iterates, it goes here. And here is my WK, a point on the valley where I have transversal intersection, because I am following this guy, which is a transversal intersection I create. And the same for the other one. So when I push backwards this guy, this guy I push backward, eventually it should hit, it should hit here. And this is my WK. But as I said, in the Birkhoff theorem, I not only need to be transversal, but I need to make sure that this is with a certain angle. Well, I solve this by pushing backwards this one and use the dynamics to say that eventually this will be basically vertical because I'm shrinking like that and doing the other way. So this has so I use many times until I am even closer to P1. So this is in the hypothesis of Birkhoff, and I'm doing the same, pushing forward in order to get that. And now I'm done, ready. The only thing I'm saying is that if you want to go from UWU to WS, you need to use a lot of things. So you go from here to there, and there to there, and there to there, and there to there, and there to there. So it is not like before that basically in one iterate everything had happened. We need to reconstruct everything so that eventually we have this situation here. Once you have that, you can basically apply the Birkhoff theorem to show that exactly what you are claiming happens. Okay. And I think I'm done. So this is the first time that Catalans did this 10 tower of 3 people in each level. And this Folra and Manillas, it means that there is 2 people, you know, there is in 2 places we put more people, otherwise we cannot handle with everything. And this is 10. And this happens in Vilafranca, which is my neighbor town. We fight each other because we don't like each other because we are close and we compete a lot, but they are very good on doing towers. So thank you very much for your attention. 44, 50.
Questions for the speaker?
I have a question. How enough is that 10 people? I can only count 8.
No, because well, there is in all proofs are some hidden thing. So on top it is 3 until the last it is 2, 1, and 1. Because the last 3 is just kids of 5 years old, so you need to be careful with them. But because why you need to be small? I mean, because you should be up there. But you know, I have to say that if you see this in reality, it's amazing how tall is this. Huh? So notice that this is, you know, this is the city hall. You are much farther. I know the guy is here. He's a friend of me.
Let's the speaker.